So next, let's move on to resonance structure practice. And so for this set of compounds, determine if they are isomers or resonance structures. And if you can recall, isomers are a set of compounds that have the same chemical formula, but the spatial arrangement of atoms in the compounds differs. And for resonance structures are where multiple valid Lewis structures are able to describe the delocalization of electrons in a molecule or ion. So for these compounds, we could see that this carbon over here has an extra hydrogen, while this carbon here does not, right? And then here we see a CH2 here, one less hydrogen than the carbon over here. And that tells us that the spatial arrangement is different. And so therefore they can't be resonance structures, and so they are isomers. So here you're asked to determine if these compounds are resonance structures or isomers, and if they are resonance structures, show how to interconvert in between them. And so right off the bat, let's see the chemical formula for these structures. And we can see that if you were to count them all up, you have 1, 2, 3, 4, 5, 6 carbons, right? On this one, 6 carbons here as well. Okay, and then the hydrogens, just by looking at it, you could tell also that it has the same number of hydrogens, so the chemical formula is the same. And I don't see any hydrogens that are in different places from one compound to the other, and so that tells us they're not isomers. And now the way we can tell if they're resonance structures or not is to look here. We see that there's a delocalization of electrons, right? In this carbon right here, on the left compound, there isn't a negative charge, and instead there's this double bond between the other carbon. But in this one, we see that there is a negative charge. So that tells us there's a movement of electrons that causes the compound to be in resonance with this one. And so the way we would show the interconversion, first I would pay attention to the negative charge on the carbon, right? And so the negative charge on the carbon tells us that there's a set of lone pair electrons. So on the left one, on that one, and then the carbon over here. Okay, and so now what we have to do is just figure out a way without moving any of the atoms around to make this compound go and become this one. So what I would do is I would take these electrons and I would use them to form the double bond with this carbon, and then that gives us here. But now that would give us a problem with this carbon, which would make sense to now move this over here, and now this carbon is negative, right? And so that's how we would interconvert to go from this one to this one. And so now we just do it the opposite way, right? So electrons go down here to form the double bond, and then the electrons from this double bond go into this carbon, and then now we have this compound. And so these are resonance structures, and that's how you interconvert. And yeah, there we go. So go ahead for this, determine if the compounds are isomers, resonance structures, or neither. And so the trick is to first count the number of atoms and make sure that you have the same amount for all the compounds. And then determine spatial arrangement. If that's the same, it tells you it's resonance. And then we'll focus on delocalization of electrons on the compounds to get the interconversion between the resonance structures. So first, I could see that just by looking at this, that the left side for all three of them is the exact same. So I'm not going to worry about that. But then on the right side, right, let's count the number of atoms. So this one, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. And each of them has one nitrogen. And so if there's going to be a difference, it would be in the number of hydrogens. So this one has 6, 8, 11 hydrogen atoms, right? And then this one has, let's see, 6, 7, 10 hydrogen atoms. And this one has 6, 7, 8, 10, right? So right off the bat, we can say that this compound right here, the relationship between this compound all the way on the left and these two is they are not the same. They're neither isomers or resonance structures, right? And so now we can just focus on these two and determine if they're isomers or resonance structures, or even now that because now we know that they have the same chemical formula, right? And right off the bat, we could see that the arrangement is different. So that eliminates the possibility of them being resonance structures, right? So here we see that this carbon doesn't have a hydrogen on this one, but this carbon does have the hydrogen. And we could also see that you know, the the hydrogen that was supposed to be here is now on this carbon over here. So we see that the spatial arrangement is different, telling us that they are not resonance structures, and so they have to be isomers. So before we've seen examples where we just had to compare two different compounds and determine if they're isomers, resonance structures, or neither. But now let's actually try and practice drawing resonance structures ourselves. So here you're asked to draw the resonance structure for the compound below and use curve arrows to show interconversion and provide a reasonable resonance hybrid for this compound, right? And so don't worry about the resonance hybrid for now. That will be explained later. But the way to approach this, first I would draw the lone pairs on the oxygen atom. So an easy way to know this, right? If it's neutral, oxygen is going to have two sets of lone pairs, so four lone pair electrons, right? And this is something you could just memorize, but if you want to actually know how to do it, it's just going to be the formal charge formula, right? So oxygen has 6 valence electrons minus the number of non-bonding electrons, which is 4, minus 1/2 the bonding electrons, 2, 4, right? And so this is gonna equal to 0, right? And so when it's neutral, it's gonna have 4 non-bonding electrons. That's just something to keep in mind. And you could always just use the formal charge formula to calculate it yourself. But anyways, we see that the carbon is electron deficient, right? And we see that the oxygen has electrons that it can use to, um, you know, do resonance. So we could delocalize like one set of electron pairs to here we could, for example, form a double bond between the carbon and oxygen. And so now what we're going to get is resonance structure like this, right? Draw the arrow showing resonance. Then we have here, okay? So all we're doing is just moving electrons. We're not actually moving any of the atoms around because that would give us isomers, right? And so here, right? Now what you see here is the carbon that was once positive is now neutral, and the oxygen that was neutral is now positive. And this is also a good way to check your work when doing resonance, is making sure that only if you start off with a positive charge that you also end off with a positive one charge, right? For example, we did that here. And so you might be thinking, how did you get the positive charge for the oxygen? Well, it's just the formal charge formula, right? So 6, that's how many valence electrons oxygen has. It has 2 non-bonding electrons, and then minus 1/2 the bonding, which is 6. So here we have 6 minus 2 minus 3. That's just 6 minus 5, which is equal to 1, positive 1, right? And so the oxygen has a positive charge, okay? And so yeah, this would be the resonance structure for this compound, and that's how you determine it. And we should show interconversion from this one into that one. And so how we do that is literally just doing the reverse of what we did. So we're just using an arrow to show the movement of electrons back onto the oxygen, which would just yield us a compound on the left again. So next, let's do the next part of the problem that's asking for a resonance hybrid. So a molecule can't be accurately represented by a single Lewis structure if electrons can be delocalized, as in this case. The resonance hybrid is a single, more stable representation that accounts for the movement of electrons, right? So it's pretty much like a weighted average of all the valid resonance structures that the molecule can have. And the way you represent this is by showing a dotted line for the movement of electrons, which causes a difference in the bonds that are created, okay? And so here, um, let's draw out what we have first, like this, and that, okay? And so we see that the only bond that's really changing is this double bond that we're forming, right? And so we would represent this by drawing a dotted line as a bond from the oxygen to the carbon. So just like this, right? And next, we'll also draw the, so this is pretty much like the two delocalized electrons that were on the oxygen in this structure, right? And so now oxygen only has one set, okay? And then this is pretty much saying that the those two electrons are being used to form this double bond, but they're also part of the oxygen as well. And so um, in this case, you would have to represent the charges on the compounds using um, partial charges. And so for both the carbon and oxygen, they're going to have partial positive charge, right? Okay. So they're both going to have a partial positive charge because we saw here in this structure, the carbon goes, or in this one, the when you go from this one to this one, from the left to the right, oxygen goes from being neutral to being positive, so that gives it a partial positive charge, and then carbon goes from being positive to neutral, and that gives it also partial positive charge. And so this would be the resonance hybrid that represents these resonance structures for this compound.